Number 7. The oxidation numbers assigned to the atoms in some organic compounds have unexpected values. Here we go with that organic chemistry again. Assign oxidation numbers to each atom in the following compounds. Note, some oxidation numbers may not be whole numbers. Now, I'm going to warn you before we get started, there's a big reason why we don't do a lot of organic chemistry in this course, because it's rough. It's rough. There are a lot of rules to learn. There's a lot of monotony, and then there's a lot of exceptions to those rules. And I don't want you guys to spend most of your time trying to learn exceptions to rules. I'd rather you try to learn the rules. But number 7 is about exceptions. So let's try it out. CO2. Each oxygen, this is a common oxygen situation, so each is going to have a -2. That's a total of -4 on this side, so that means that carbon is going to have the +4. No problem there. That makes sense. Looking at methane here, again, hydrogen's listed second. But that's really more of a situation. It's convention because it's an organic molecule. They list the central atom first when you're talking about organic molecules. So we look at carbon on the Pauling scale, 2.5, hydrogen 2.1. That means that that carbon is more electronegative than hydrogen. That means that carbon's going to be pulling on those electrons more strongly, meaning those electrons are going to be closer to carbon. So it's going to be carbon with the negative oxidation number. So that means that hydrogen's going to have, I might as well just write it here, a +1. There are 4 of them, so that means that carbon is going to be balancing that out with a -4. -4. All right. C, glucose. Now we're getting a little bit crazy if we want to look at the entire molecule. But let's see if we can work this out just by using our rules. So we have hydrogen here, but it's not in front or in the back, so we can't really use any of our trends there. But we wouldn't want to because these are exceptions. Okay, these are organic. When we look at the electronegativity values, we see that compared to carbon and oxygen, hydrogen has the least electronegativity, so it's definitely going to be a +1. Definitely going to be a +1. Oxygen is much more electronegative than carbon, so oxygen is going to definitely have a -2. And so all that's left is what's carbon? What's carbon going to have? So I have 6 oxides coming in at, or oxygens coming in at -2, so that's a total of -12. I have 12 hydrogens coming in at +1. They're already balanced out. They're already balanced out. And so, because they're already balanced out, that means that carbon has an oxidation state of 0. And in this situation, what's happening is carbon is attracting the electrons from the hydrogens, but oxygen is attracting the electrons from the carbon. And so even though carbon is having some electrons move towards it, it's also, at the same time, having electrons move away from it. And lastly, our good friend is hydrocarbon, propane gas. Okay, a 3-carbon chain. Again, we're going to start by identifying that hydrogen has a +1 oxidation state because it's much less electronegative than carbon. But here's the question. There are 8 electrons available to be pulled towards 3 carbons. 8 electrons to be spread among 3 carbons. No matter how you try to divide this out, this isn't going to be a whole number. And so what we say here is that carbon is going to have an oxidation state of 8/3. Each carbon is going to have 1/3 of the total available electrons. There are 8 available electrons to be pulled on here. That's going to be divided among 3 carbons. Right? And so that's why we have the 8/3. It's negative because those electrons are moving towards the carbon here. And again, these are exceptions. These are not things that, especially this carbon chain here with propane, is not something I'm going to test you on. I just wanted to include this for overall concept understanding.